All right, there's a question about quiz tomorrow. So you're at least semi-familiar with if charts and the patterns there, okay? And so that might be an expectation, something along those lines. What was one of the patterns that we discussed yesterday with regard to if charts? Run that by your neighbor real quick, and then I'm going to bug you. There's kind of two main patterns I'm looking for, okay? Two main patterns. So let's Power School pick on, oh goodness. Hey, Dickens, what's your group name? Sausage. Let's fix that quick. Sausage. Bullish sausage? Cancel. Better save that. All right, now we're good. Seating chart. All right. Boop. Hey, Tan. Oh. Hey, oh. Hey, Jeff. Oh. Hey, Parth. What's one of the patterns on an if chart? The total area is the same. Okay? So can you expand on that a little bit? Okay, run that by your neighbor. Like, say a little bit more. Expand on that area. Total area is the same. Boop. PB. Can you expand on that slightly? Total area where is the same? Okay? Final. All right, so the total area is the same on the initial and final. Okay? What's something else that we picked up from if charts? Let's hear from Spencer. Let's hear from Spencer. Let's hear from Parth. All right, cool. What else do we need to know about if charts, buddy? I'm looking for units. I'm looking for other patterns.
The unit, like the total area would
be the unit for the area is, yeah, because you're taking mass times velocity, kilogram meters per second, okay? And again, that's because MVP, mass times velocity equals momentum. Okay? They probably don't spell it right over at City High, do they?
Yeah, probably not.
Probably not.
I don't think they do the P momentum thing.
That's sad. All right. Total area is the same on the initial and the final. The unit for the area is kilogram meters per second. All right. I'm fishing for one other pattern here we talked about a little bit at the end yesterday. Hey, Hey, Peyton. It plays favorites. What can I say? You and Parth. All right. So the total area is the same, and this pattern kind of explains why the total area is the same. What's happening to the individual gliders with regard to their changes? Okay, Anastasia, what did she say? Okay, the changes for the individual objects, right? For the individual objects are the same. Same how? Same number? Works for me, man. Changes for individual objects are the same number, but opposite sign. All right, cool. So those are kind of the important understandings on an if chart. And then we expanded from there. We looked at the equation from the unbalanced force particle model, FU equals MA. And because A is change in velocity over change in time, that's how we would calculate it. We can say FU equals M, change in V, change in T, and then multiply both sides by T, and you get this thing, mass times the change in velocity, which is mass times VF minus VI, okay? And that goes along. All right, so that goes along with this thing right here. We're taking mass times velocity. You're taking mass times final velocity and multiplying that by, mass times final velocity and then subtracting mass times initial velocity. That's finding the change in momentum. Do that in a different color. I need like a quick key for ink. So that's the change in momentum. And again, Peyton mentioned the changes for the individual objects are the same number but opposite sign. And part of the reason for that is because when they're colliding, when they hit each other, okay, when they're interacting with each other, they're putting the same size forces on each other, okay? And that's because forces come in pairs. And so they're experiencing the same amount of unbalanced force for the same time interval. They're going to have the same change in momentum. So this side of the equation is called impulse. Okay? Impulse equals change in momentum. Equation-wise, that's pretty much it. Okay, when you got an if chart, you find the area of the rectangle, that's the momentum. You find the difference in the area from the final to the initial for each object, that's the change in momentum, and that's equal to the unbalanced force times the time. Now, units-wise, we didn't talk about this yet, but unbalanced force, that's going to have what units, Brody? Newtons. And time, that's going to have what kind of units, Brody? Okay. So that's going to be Newton seconds. Momentum, I'm taking mass times velocity. Okay, I can't do the Peyton thing anymore. Who are our other name twins? Do we not have any more? That's lame.
Wait, what happened to Peyton?
Peyton's in Mr. Muller's class now. Sad face. All right, so change in momentum, I'm going to have mass times velocity. I'm going to have kilograms times meters per second. Are those two things equal? Well, let's have a think about it. Newtons is kilograms times meters per second squared. Okay, that's a Newton. If I multiply that by seconds, what am I going to get? So I take kilograms times meters per second squared, multiply that by seconds. Oh, yeah. Thing. And I'm going to get kilogram meters per second. Those things are equivalent forms. Product of force and time is the same as product of mass and velocity. Those yield the same units. All right. So then, what we're going to hit up today is a little bit of practice with this in advance of the quiz tomorrow. And let's see, another physics canvas. Which one? This astronaut. All right. All right, so I got some if chart whiteboard problems for you. I'll get this headed your way. If you want to Have a go with this with your friends and neighbors. You got questions on how to do stuff. Now's the time to ask.
Oh, I'm sorry.
What's up? Good hands, sports. All right. All right, so I'm going to give you a little bit of work time here. Have a go at some of these. There are in total 7 problems. And the back page is all graph paper, is that true?
No.
No.
Yeah,
Graph paper.
it is true.
You can like draw the diagrams there if you want to. You don't have to, so you don't have to draw a scaled if charts anymore. I just wanted that so visually you can kind of see that when we did those for the air track. You just need to make sure you're labeling them now. Okay, you know the important things to pay attention to on an if chart. So draw if charts for these problems and see if you can figure out what's going on there. Let's take a look at this first problem there. Who's wearing Vans? Nobody? Oh, Gary? Vans? Cool. All right. So I'm going to put him on the skateboard. And then I'm going to give him this oxygen tank. You wore the shoes, you better not fall in them. All right. So he's going to hop on this thing, of course, sir. And then I'm going to give him this bowling ball, okay? And I'm going to scooch him a smidge. All right. So right now, he and the bowling ball have a total momentum of, relative to the room, right? Like his velocity is 0, the bowling ball's velocity is 0. So if you're drawing an if chart, what's the total area on the eye? 0, okay? Now, they're not going to collide, but they are going to interact, okay? This is why I'm trying to use that word interact. He's not colliding with the ball. He's like opposite of colliding with the ball. He's going to push the ball at me. So go ahead and give me like a chest pass. Yeah, bro. I played sports. Chest pass. For reals this time. What happens after he interacts with the ball? Okay? So once more with feeling. What does he do? You noticing? I think you got to do it again, man. Get something on it this time. Snap the wrist, right, Bron? All right, there we go. So what happens after he throws the ball? What happens to him? He goes backwards. What has a greater velocity? The ball clearly is going faster, right? Okay? So the ball's going this way at, I don't know what, like 50 miles an hour or something like that. Like he's really putting some zip on his paper. Okay? He's going that way slower. So can you kind of in your mind, like do a mental, you can hop off there. You know, do a mental if chart for that. We talked about the first one, there's no rectangles. What's true of the rectangles on the second one we do that? Think about how the force that he puts on the ball compares to the force that the ball puts on him. Think about the time the force acts on the ball, the time the force acts on him. So what's got to be true of those rectangles on the second one if initially they're adding up to 0? So employ that on this first problem here with the astronaut and the oxygen tank. Ooh, and then we need to watch that movie Gravity. Have you seen that movie Gravity? Yeah, I gotta bring that. Whoa, that's not like a, oh, a bag of cookies. Yeah. All right. So we can kind of roll through this one together. So we got an astronaut. The mass is 80 kilograms. You got an oxygen tank. It's 10 kilograms. So here's what I'm saying. I'm not scaling these anymore because nobody's got time for that. Initially, their velocities are 0. So for I, total P equals 0. So now when I go to draw my F, I already know the total P should equal Parth?
0.
Yeah. All right. So I'm over here, and the tank's going 2 meters per second. So this is 10 kg, and it's going 2 meters per second. So that's 20 kilogram meters per second. What do I already know about the astronaut then? Area's got to be 20 kilogram meters per second? Nah. Area's got to be negative 20 kilogram meters per second, okay? And I know that the width of it is 80 kilograms, so what's the height of it to have the area be negative 20 kilogram meters per second? So this is 80 kilograms times VF. VF equals negative 20 kilogram meters per second divided by 80 equals 2 over 8, 1/4, negative 0.25. Winner, winner, chicken dinner. Is that right?
Sounds right.
So that's the final velocity of the astronaut. Did anybody get to see the astronaut the other week? There was an astronaut here. Just me? You saw the astronaut?
No, I was going to ask, what's the units by that 2?
By that 2,
Like on the final?
that's okay. You're talking this 2?
Yeah.
So this is velocity up here. Sorry, I should have labeled better. So that's meters per second. And then on here, this is mass.
So you're saying times velocity? What's
Yeah.
the VF?
Of the
Like the negative 20 kilograms meters per second equals 80 kilograms
times VF, so the final velocity of the astronaut. Yeep, yeep. All right, once you're done with your closing patterns, you can get with the rest of it.
I finished reading 10 pages.
Sure.
Yeah, it's actually a really good book. Have you read it?
Get it done.
It's just orange. It's really good. Everyone that's had creation.
What color? We'll get those square colors.
It's just about like life lessons.
We'll do it on iron. Right? So whatever the velocity is, multiply by 80. That's what the astronaut's mass, the astronaut's final velocity.
That's the only way to just solve it. That's like it's the way. And then have the you'll see it in the other one. So what whatever the area is on the initial, that's what the area in the final. It might be a problem where you know the area on the final, you gotta figure out what was the area on the initial. I think that's what I'm understanding. But like that velocity was slow, but when you saw here, you throw that bowling ball, was fast. He was slow.
Okay, should we do one of these checks?
What's up? Got him. Johan. What's up? For you.
What would he call me? Program mowing the flags on your dog on his son, Throckmorton, took a 50 to an object to speed of 30 meters per second. The rest has to speed along and merges with the 18. Okay, so the initial velocity is 30 meters per second. And the final is 18.
So is that before or after the
But I don't know how to organize anything else.
So that would be part of the I. Johan.
So I'm going to read.
That's negative 12 with carrying velocity. Minus 12 so 0.5
I never did. Alright, so in that area, that's the only area. You can just solve it quantitatively, but if you have to present it, solve it.
Yeah, I just know how to do it this way.
Well, I don't, that's understood. Good deal.
You need help? What is it? All right.
All right, boss. How many grams have you chosen? You've got 50 grams. You've got.
Yeah, no, I didn't change it. I got it.
Okay. You were just trying to. Let's explain this. Alright, so you got a melon on top of the sweet.
Yeah.
So that's correct. So that's got no block. So when you're doing this problem, you want to establish what is the interaction. So like with Alicio and the bowling ball, the interaction. So we want to pay attention to what's happening before, what's happening after. The conditions on that air track, the interaction is when they pull out. What was happening before. So here, what's the interaction? So that would be one. Yeah. What's the arrow 8? What makes this color? So there's our arrow. So before the arrow, melons are sitting on the phone. What's the arrow before this? There you go. So we want to have that represented on 0.05 billion. The height of that rectangle is 30. You don't have to scale. Skinny rectangle. Ooh. They're all not one drop. All right, so that establishes what the total area is. 5.05. Cody, what do you want to talk about? I'd say. That's going to be the total area. So our pattern that we established in the lab is if we know the total momentum on the initial, that has to be the total momentum. We have the same total momentum. Maybe, let's see. 1.5. Okay, cool. So then the total area here's got to be 1.5. So if we know is that arrow's going to be 8, that's got to be 6. Wait. Oh, momentum here's 0.9? Or just for that one? Okay, so this has to be 0.6. Yeah, 0.6 goals. Yeah, gotcha. Yeah, I think that's right. So before the collision, correct. Correct. Plus 0. So then, yeah, we don't have so on the initial, this one. Finally, after the interaction arrow, so that.
So what you do this one?
Still has to see.
Even if they do the initial,
This.
all I do is I'll just go to find
No.
I'll wait for you.
Some of that.
what does player returns 30 meters per second shot straight at average 25
We want to know about the force. So you want to know about the force. You gotta look at the other equations.
Hey, friends, you got a couple of things you're running on here. Okay, one of them is this if chart thing that we talked about. The other thing is that impulse change of momentum discussion that we just had. So like that last problem on the first page, you've got information about change of momentum and time, and it's asking you about force. All right, so let me bring you back up to that quick. Let's do a little Simon Says, okay? Simon Says, stand up. Simon says if you've got knee or back problems, sit this one out. Otherwise, Simon said get your shoes on. All right, knee or back problem, you sit this one out. Okay. So Simon says if you're on like a state title winning dance team, you can probably freaking handle this. We're crying out loud, Patty. So what we're gonna do is jump in the air and land. Okay, you ready? All right, jump. Simon didn't say jump, donkeys. Jeez. All right. Simon says jump into the air. Okay. Now I heard some grunting over here, but generally that sounded okay. Let's try it again. All right. I thought I was a 42-year-old, but all right. Simon says jump as high as you can. Okay, ready?
If you're able to do that, land like yeah. 80's going to do some kind of, I don't know what that's called here, a vest or something like that. All right. Nobody hurt themselves that time. So what I want you to switch this time is instead of landing by bending your knees, I want you to keep your knees locked. Now I want you to keep your knees, hang on. To prevent catastrophic. Simon didn't say do that yet, you donkey. All right, I want you to jump without bending your knees too. So you're just going to kind of like push off with your little flippers, okay? So you're just going to give it a little, but land, jump and land without using your knees, okay? Try that real quick. Right, now the faces don't look so happy, right? You're like, if you're me, you're feeling that in the lower back a little bit, right? You didn't jump as high. Why did it hurt more? Okay? And so it has to do with this. You're still jumping in the air. It's still the same change in momentum. But if you don't bend your knees, you stop more what? Abruptly. You stop more abruptly. It takes less time. So you got a certain change of momentum you're trying to cause. Okay, that takes a force acting for a time period. If you make that time period really small, what does that force have to do to cause the same change of momentum? It's got to be big. Big FU. That's why your back hurts, okay? Whereas I could jump off this table and not like blow up my knees as long as, or my back, right? As long as I bend the knees, I extend the time, and if I make T bigger, what happens to the F? Get a smaller F. I am not decreasing the change in momentum. I'm still stopping, but by using a bigger time, I can get away with using a smaller force. What are some other examples of that in everyday life? Can you run that by your neighbor? What are some other examples where you either extend the time to decrease the force or decrease the time to increase the force? Slowing down at a stoplight. So you press on the brakes slowly, okay, or you slam on them or like put it into a wall. It still stops the car. Still the same change of momentum. But if you stop your car by using a wall, that's probably only one time you can do that, right? So use the brakes. And if you just gently press on the brakes, it takes a longer time to slow down, but it doesn't throw you forward into the dashboard. So that's a good one. What's another one? Wrestling team. You ever been thrown to the mat? No? Okay, never mind then. These guys are too good. You throw people to the mat, okay? Contrast throwing people to the mat with throwing people to the concrete floor. How's that going to end differently? Yeah, that mat's got some give to it, right? You're going to be able to get back up, right? Or keep throwing to the floor right here. Now you're out, right? That's it. That's the end of your day. Okay? Other examples like that. Doesn't have to be from the world of sports or driving. Let me throw a video your way here, see if I can give you some idea of what's going on. So think about all the different ways video. Okay, so hey, check this out, friends. All right, so this was like some kind of a celebration of like 50 years of the highway transportation safety, something or other. So you got a 2009 Chevy Malibu versus a 1959 Chevy Bel Air. Which car would you rather be in? Probably neither is probably the safe choice. So think about the different ways that this idea of changing the time to change the force shows up in automobiles. Run that by your neighbor really quick. Like, what are some automotive design aspects
So modern automobiles, what do they have to help you not be dead in a car accident? Airbags, that's a big one. What else? Seatbelts.
It's like a crash impact.
The frame acts like your knees, right? Yeah. So the frame kind of acts like your knees to slow it down over a longer time. Is that what you were going to say? Crumple zones, they call it, on the front of the car. Okay. So the car is designed to give kind of like your knees. Back in the day, they designed the steering column like a javelin, so it would just push into your face and remove all your teeth. Okay. Nowadays, steering columns are designed to break away. So you notice the steering wheel doesn't jump up into their face. In fact, there's a pillow. So if you're in this car, this crash is survivable. Look at that. The steering wheel does not push forward. Airbag deploys. Now you got all those airbags around you. But this is like a worst case scenario type of crash. Offset, driver to driver. This is it in slow motion. Oh boy. That'd be not great. All right. I'll shut up and let you get back to your worksheet.